Planets are always moving. They are in a constant state of motion, traveling through the vast expanse of space. This movement is not random but follows specific patterns and paths that have been studied and understood by astronomers for centuries. They orbit stars just like Earth orbits the Sun. This orbit is a result of the gravitational pull exerted by the star, which keeps the planets in a consistent path around it. The concept of orbiting is fundamental to our understanding of how solar systems function. These orbits are not random, they follow specific paths, shaped by the force of gravity. Gravity acts as an invisible hand, guiding the planets along their paths and ensuring they don't drift off into space. This force is what keeps our solar system stable and predictable. Understanding planetary orbits helps us grasp the fundamental workings of our solar system and the universe beyond. By studying these orbits, scientists can predict the positions of planets, understand their interactions, and even discover new celestial bodies. It's like a cosmic ballet, with planets swirling in a graceful, intricate dance. Each planet moves in harmony with the others, creating a beautiful and complex pattern that has fascinated humans for millennia. Imagine our solar system as a giant stage. The Sun, a blazing star, takes center stage. It is the anchor of our solar system, providing the necessary gravitational pull to keep the planets in their orbits. Around it, the planets twirl and spin, each following its own invisible path, or orbit. These paths are determined by the gravitational forces at play, ensuring that each planet remains in its designated position. These orbits are crucial because they determine a planet's distance from the Sun, which in turn affects its temperature and potential for life. The closer a planet is to the Sun, the warmer it is, while those farther away are colder. Planetary orbits are not perfect circles. They are slightly elongated like ovals, which we call ellipses. This elliptical shape is a result of the gravitational forces and the initial velocity of the planets when they were formed. They are slightly elongated like ovals, which we call ellipses. This shape means that the distance between a planet and the Sun changes as the planet moves along its orbit. This elliptical shape means that a planet's distance from the Sun varies throughout its orbit. At certain points the planet is closer to the Sun, while at others, it is farther away. This variation affects the planet's climate and seasons. When a planet is closest to the Sun, it moves faster. When it's farther away, it slows down. This change in speed is due to the gravitational pull of the Sun, which is stronger when the planet is nearer and weaker when it is farther away. Learning about planetary orbits is like learning the steps to this cosmic dance. Each planet has its own rhythm and pace, contributing to the overall harmony of the solar system. It allows us to predict the positions of planets, understand the history of our solar system, and even search for life on other worlds. By studying these orbits, we can gain insights into the past and future of our cosmic neighborhood. So, let's delve into the fascinating world of planetary orbits and unravel the mysteries of these celestial motions. By understanding the intricate dance of the planets, we can appreciate the beauty and complexity of our universe. Centuries ago, a brilliant astronomer named Johannes Kepler cracked the code of planetary motion. Kepler's journey was not an easy one. Born in 1571 in the Holy Roman Empire, he faced numerous challenges, including poor health and financial difficulties. Yet his passion for the stars and his relentless curiosity drove him to pursue a career in astronomy. He formulated 3 laws that describe how planets move in their orbits. These laws were groundbreaking at the time and laid the foundation for modern celestial mechanics. Kepler's work was built upon the meticulous observations of Tycho Brahe, a Danish nobleman and astronomer who had amassed a wealth of data on planetary positions. These laws, known as Kepler's laws of planetary motion, revolutionized our understanding of the solar system. Before Kepler, the prevailing belief was that planets moved in perfect circles, a notion that had persisted since the time of the ancient Greeks. Kepler's insights challenged this long-held view and provided a more accurate description of planetary motion. Kepler's first law states that planets orbit the Sun in ellipses, with the Sun at one focus of the ellipse. This was a radical departure from the circular orbits proposed by earlier astronomers like Ptolemy and Copernicus. The elliptical nature of planetary orbits meant that the distance between a planet and the Sun varied throughout its orbit. This law shattered the ancient belief that planets moved in perfect circles. It was a significant shift in our understanding of the cosmos, one that required a new way of thinking about the forces that govern planetary motion. Kepler's first law laid the groundwork for the later development of Newton's theory of gravitation. It revealed the true nature of planetary orbits, with their slight elongations. These elongations, or eccentricities, vary from planet to planet, with some orbits being nearly circular and others more elongated. Understanding these variations was crucial for accurately predicting planetary positions and movements. Kepler's second law explains how a planet's speed changes as it travels along its elliptical path. This law, also known as the law of equal areas, describes the relationship between a planet's velocity and its distance from the Sun. It was a key insight that helped astronomers understand the dynamics of planetary motion. It states that a line connecting a planet to the Sun sweeps out equal areas in equal times. This means that a planet moves faster when it is closer to the Sun and slower when it is farther away. The varying speed of a planet along its orbit was a concept that had puzzled astronomers for centuries. This means that a planet moves faster when it's closer to the Sun and slower when it's farther away. This variation in speed is due to the gravitational pull of the Sun, which is stronger when the planet is closer and weaker when it is farther away. Kepler's second law provided a clear and concise explanation for this phenomenon. Finally, Kepler's third law establishes a relationship between a planet's orbital period, the time it takes to complete one orbit, and its average distance from the Sun. This law, also known as the harmonic law, was a major breakthrough in understanding the mechanics of the solar system. It provided a mathematical framework for predicting the motion of planets. It states that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This relationship can be expressed mathematically as p squared equals sine a cube, where p is the orbital period and a is the average distance from the Sun. This equation allowed astronomers to calculate the orbital periods of planets with remarkable accuracy. This law allows us to calculate a planet's orbital period if we know its distance from the Sun, and vice versa. Kepler's third law was instrumental in the development of celestial mechanics and paved the way for future discoveries in astronomy. It remains a fundamental principle in the study of planetary motion to this day. Kepler's laws described the how of planetary motion, detailing the elliptical orbits and the varying speeds at which planets travel around the Sun. These laws were groundbreaking, providing a mathematical framework that could predict the positions of planets with remarkable accuracy. However, while Kepler's laws were incredibly useful, they didn't explain why the planets moved in such a manner. What was the underlying force that dictated these celestial dances? It was Sir Isaac Newton who provided the why. Newton, one of the most influential scientists in history, sought to understand the fundamental principles that governed the universe. His curiosity and intellect led him to uncover the force that not only explained planetary motion, but also unified the heavens and the earth under a single theory. He discovered the force that governs the movements of planets: gravity. This invisible force acts between all objects with mass, pulling them towards one another. Newton's insight was that the same force causing an apple to fall from a tree also governs the motion of the planets in the sky. Newton's law of universal gravitation states that every object in the universe attracts every other object with a force that is proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. This elegant equation not only explained the orbits of planets, but also the behavior of moons, comets, and even the tides on Earth. In simpler terms, gravity is a force of attraction between any two objects with mass. This means that everything from the smallest particle to the largest star exerts a gravitational pull on everything else. The strength of this pull depends on the masses of the objects and the distance between them. The more massive an object, the stronger its gravitational pull. For instance, a massive planet like Jupiter has a much stronger gravitational field than a smaller planet like Mars. This is why Jupiter can influence the orbits of other objects in the solar system, including asteroids and comets, and the closer two objects are, the stronger the gravitational force between them. This is why the Moon, despite being much smaller than the Earth, has a significant effect on our tides. Its proximity to Earth means that the gravitational pull is strong enough to cause the oceans to bulge, creating high and low tides. Newton's law of gravity explained why planets orbit the Sun. The Sun's immense mass creates a powerful gravitational pull that keeps the planets in their orbits. Without this gravitational force, the planets would simply drift off into space. The sun's massive size creates a strong gravitational pull that keeps the planets in their orbits. This gravitational force acts as a cosmic tether, ensuring that the planets remain in a stable, predictable path around the sun. The planets are constantly being pulled towards the sun, but their own forward motion, combined with the sun's gravity, creates a curved path, an orbit. This delicate balance between gravitational pull and forward momentum is what keeps the planets in a continuous dance around the sun. Newton's discoveries revolutionized our understanding of the universe. Before Newton, the motions of celestial bodies were shrouded in mystery and often attributed to divine forces. Newton's work provided a scientific explanation that could be tested and verified, laying the groundwork for modern physics and astronomy. They provided a unified explanation for the motions of planets, moons, comets, and even the tides on Earth. This unification was a monumental achievement, showing that the same physical laws apply both in the heavens and on Earth. Gravity became the invisible force that sculpted the cosmos, holding everything together in a delicate balance. From the formation of galaxies to the orbits of planets, gravity is the fundamental force that shapes the universe, creating the intricate and beautiful dance of celestial bodies that we observe today.